Okay, so today we're going to talk about sampling and sampling distributions. And so by now you should be very comfortable with the normal distribution. You should be able to use a z-table. Ideally use either kind of z-table. If you practice with both, that'll improve your understanding for sure. I'm going to clear some stuff out of the way here while I talk. You should be able to look at a graph that looks like this. It's got an x down here. This is the curve. It's got a mean, a standard deviation. Sorry, my drawing skills are a little off today. You should be able to figure out what this area is, right, when they give you the other three. In addition, you should be able to figure out what this x1 is if they give you this area. Once you can do that, then, well, now you have the technical skills that we need to move forward. Okay, now, until now, what we've been doing with the normal distribution is we've been looking only at populations that are normally distributed. Right? And what we really care about is characteristics, like height, weight, etc., which, remember, we called x. And we care about characteristics of the population. We might care about the mean value of the characteristic, but we care, or the dispersion of it, which we use standard deviation to measure dispersion. We care about that characteristic of the population, right? The likelihood that they're going to buy something, their height, their weight, the filling weight of or the bottles we're producing. Now, in practice, most populations, right, most characteristics are not really normally distributed, right? You might have all sorts of different distributions. Now, if this is x, you might have a distribution that looks like this. You might have a distribution that looks like this. These are all distributions, right? You might have a bimodal distribution that has two humps. You might have a uniform distribution. And all this stuff up here is assuming that the distribution of a characteristic followed this bell-shaped curve. Right? Now, there's a family of these curves, but still, that's only one family of curves, one family of possible distributions. There are lots of possible distributions, right? We talked about the distribution of faces on pips on a die, which, you know, looks like this. Doesn't look anything like a normal distribution. Now, if that was all that the normal distribution was good for, was talking about these kind of populations, these type of characteristics, then it wouldn't be so famous. But it is justly famous. We'll discuss why. Okay. So, one of the most common things we care about is the mean value of something in the population. But it's the average, right? What on average is likely to happen, or what on average does this relationship look like? And so one of the things we care about is the sample mean. Why? Well, if you recall, we talked about populations being large and therefore expensive to count. Samples are small, right? This is why people do focus groups. Samples are small. They're relatively cheap. Problem is that samples don't tell you that much, right? They only tell you, well, without some powerful math, they only tell you about what 20 people think or something like that, right? Still, we can take a sample and we can look at the mean within a sample, and we call that the sample mean. And it's denoted with x bar, right? And it looks like this. We can calculate the sample mean. We did it already in the descriptive statistics section. The formula for x bar is equal to, draw a little fraction bar here, it's the sum from I equals 1 to n of x sub I all over n. Now, in practice, what this really is, it's the sample mean of n people, right? If you had more people, well, that formula would change a little bit because that n would be different. And when we add them up, you'd add them up differently. Now, what happens is, I'm going to draw three distributions for you. Turns out that, let's just say we have some population distribution. And it looks like whatever you want. It can look like whatever you want pretty much, right? It can be bumpy. It can be any of those things, right? Well, now we take a sample. And then within our sample, we have another distribution. Now, this is going to be finite, so we're going to have a couple people who are this height, a couple people who are that height. It's going to look like this. This is, sample distribution. Look something like this, maybe. Who knows? But if it's a random sample, we draw a random sample, what that means is that we're going to have some mean value. Okay? Draw a random sample of, say, 10. Okay? Well, it's going to have some mean value, right? You can draw a line here. It turns out that this will be your x bar, right? Somewhere in there. Maybe your mu is over here. This is your true value. Your x bar is going to be your guess, right? So your sample mean is your best guess of the population mean. So if I asked you, what's the average height of the whole population of college students, and you picked 50 college students and measured their height and found the average, well, then that average would be your best estimate of the population average, right? The problem is that it's going to be wrong. It's okay. It's the best you can do, right? It's the best you can do. It's still wrong, but it's going to be wrong in a particular fashion. It turns out that it's going to be random, right? What you're essentially doing is you're picking 10 random people, right? And what that means is you get some random variation. So that x bar is a random variable. The mean is a random variable. X bar is a random variable. And it turns out that as n gets large, meaning as this goes from 10 to, say, 100, what happens is that your distribution of x bar now, not of x, but the distribution of x bar is a random variable, the sampling distribution of your sample mean approaches a normal distribution. And that is really nice. What that means is that no matter what this looks like, and essentially no matter what your sample looks like, as long as it's big enough and it's randomly selected. I didn't even draw 10 dots there. Here, I'll draw a 10th dot. As long as it's randomly selected, the mean will be drawn from a bingo cage that looks like this, right? You essentially say, okay, well, each bingo ball has a number on it, and that number is the mean of 10 people's height, 10 randomly drawn people's height. You do that over and over and over again. This curve right here, this normal distribution, this is what that bingo cage looks like. It's full of stuff. Now, I'm going to draw this bigger so that you can actually see what the distribution looks like. Okay, let's pick a different color. We can use purple for now. So this is the sampling distribution of x bar. It's normally distributed, okay? And the mean, the expected value of x bar, which is right here, E of x bar, the expected value of x bar, which is the mean of the x bar distribution, sorry, I should put this down here, is equal to the mean of the overall distribution. That's what it is. It's equal to the mean of the overall distribution. That means that x bar is an unbiased estimator of x. And as n gets large, sigma x bar, the standard deviation of this, is equal to sigma x divided by the square root of n. What that means is that it doesn't matter what the shape of the population distribution is. As long as we have a large enough sample, we have a normal distribution of our sample means, which looks like this. So that's the way to think of it. For 10 people, it's going to be less normal and it's going to be more spread out. As this gets larger, as n gets larger, the square root of n gets larger, this gets smaller, which means that this gets tighter and tighter, and it becomes more and more succinct and normal. Looks more like that. Little by little, it gets tighter and tighter. So that is the beauty of sampling distributions. That's the beauty of the normal distribution, is that it comes up all the time because x bar is distributed normally. And so before, when we were saying, well, we have to assume that something is normally distributed, now we don't have to. We know that the sample mean is going to be normally distributed. And it's going to be normally distributed with mean mu x is equal to, mu x bar is equal to mu x, and standard deviation sigma x bar is equal to sigma x over the square root of n. Okay, so what does this mean for solving problems? I'm not going to do any practice problems on this particular video because I'm running a little bit short of time, and I want you guys to just get the intuition for now. But what this means is before they gave us 3 of these 4. Mu x, sigma x, x, and p, and asked us to find the 4th. Well, now what they're going to do, and what they did to make that possible was they said, assume it's normally distributed. That is not a safe assumption. So now, fortunately, we can relax it. What these new problems will look like is this. They give us 4 out of the 5. And then they ask us to find the 5th. And they don't have to make any assumptions. We don't have to make any assumptions, right? If they give us the mean, the population mean, the population standard deviation, x bar, and sample size, right? The sample mean and the sample size, as well as some area, any of those 4, well, because of what's called the central limit theorem, and that central limit theorem is what proves that x bar is normally distributed. Because of the central limit theorem, we don't have to make an assumption about the distribution of x. This means x bar is normally distributed, so we don't have to assume the distribution, which is very liberating. It gets us closer to reality, to a real model. Now, the nice thing about this is also that this works for another characteristic of populations. And I think I have time, yeah. So population proportions, this also works for. So for population proportions, which are P, given by P usually, we also have a sample proportion, which is P bar. The way we define P bar is, well, it's let x be number of people or observations with the characteristic in question. Now that could be, number of men, number of people who like the color green, whatever. Well, if that's x, then p bar is x over n, where n is our sample size, right? So that could be like 30 out of 100, or what have you. Okay. I hope that's intuitive. If not, please send me questions. Well, if we have a sample proportion, what we can say is that p bar, if n is large, then p bar is normally distributed. And the mean is p. The mean is the true population proportion. And the standard deviation is, hold on, where's the standard deviation? Sigma p bar is equal to, there we go, square root of p times 1 minus p over n. And n has to be large enough. Okay. So that's that for sampling distributions. I'll draw p bar quick. Draw the sampling distribution of p bar quick just so you can see it. But that's all the stuff you really need to know to be able to do some work. You can see that essentially these problems are going to be the same as normal distribution problems. It's just that instead of drawing the distribution of x or p, we're now drawing the distribution of x bar or p bar. And that distribution is centered around this mean. And then it has a standard deviation, which is going to be equal to whatever. Look on your formula sheet. Look on these slides that I'm posting, and have fun working the problems. I'll post a few practice problems when I get a chance, and I'll be posting more videos soon. Thanks, guys. Talk to you in a bit.